Hi, everyone. Welcome back to this week's GOCC. Today we have Mia Smith from the University of Michigan speaking about electroid varieties and the Lagrangian Grassmannian. Before we get started, let's recall our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. With that, Mia, whenever you're ready.
Awesome. Hi everyone. I'm Mia. First off, thank you to the GOCC coordinators for like all of the work you do to make this seminar happen like every single semester. It's awesome. Yeah, I just started coming to some of these this semester and it's been really delightful. And also thank you for inviting me to give a talk today. I'm really delighted to share some recent work with my collaborators Dawei Shen and David Speyer, who are both at the University of Michigan, and talk about a project we've been working on electroid varieties and the Lagrangian Grassmannian. Um, I'll feel free, like, at any point to like stop me with questions. If I'm not seeing your hand raised, like you can just unmute yourselves. Okay, so before I kind of dive into kind of the background information, I want to give you a high level picture and kind of a slogan for kind of what you should be thinking about. What is the key takeaway of the talk? So here is the big idea. The big idea is that we have a positroid stratification of the Grassmannian via positroid varieties. What we look at in our kind of project is how electroid varieties stratify the Lagrangian Grassmannian. So you can think of this as being taking the type A kind of result and generalizing or extending to type C. So that is kind of the big slogan. So here's how the structure of the talk's going to go. I'm going to spend some time giving some background on what the first statement means. Positroid varieties stratify the Grassmannian. Then I'll introduce the notions of the electroid variety, how it connects to the Lagrangian Grassmannian, and finally look at kind of some of our results. And with the remaining time, give you kind of a combinatorial flavor of some of the sort of combinatorial guts that are underlying like a lot of our results. So without further ado, let's get going and let's talk about the Grassmannian. So this is going to be a very fast crash course, but just recall that the Grassmannian, GRKN, is the set of k-dimensional subspaces of an n-dimensional vector space. This can have the structure of a manifold. It can have the structure of a projective variety. There's kind of a lot of different ways you could think about it beyond it just being like a set. And one thing is, how do we represent these kind of elements of the Grassmannian? One particularly classical way is to think of an element as a full rank K by N matrix. And you can think of each row as kind of representing a vector in the subspace. And so this matrix needs to be full rank to be K-dimensional. And well, this is kind of a nice thing, a way to think about it. The problem is that there are many, 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 many matrices which all represent the same subspace. So we often work with elements of the Grassmannian in a different way, using these things called Poincare coordinates. So if we look here, we can take there's an embedding of the Grassmannian into projective space indexed by all k element subsets of 1 through n. And the embedding works as follows. You take your matrix, and what you do is you map it to a string of coordinates indexed by the subsets. And what each coordinate is it's the minor indexed by columns I. And this is actually going to be well-defined and an embedding. So let's look at a quick example. So here I have my matrix. If I want to compute the first Poincare coordinate indexed by 1, 2, well, I take this submatrix with columns indexed by 1, 2, and it's going to have determinant AB. Okay, now I go and I look at the minor index by 1, 3, and I see, oh, well, column 3 is a 0, so that's going to be 0. And in fact, every Poincare coordinate that has a 3 in it in the indexing set is going to be 0. Now I look at 1 and 4. Oh, that's going to have determinant 0. And finally, I look at columns 2 and 4, and that's going to have determinant negative BC. And this is going to define our Poincare coordinates. And it is well defined in projective space, so up to some scaling. Okay, great. So that's the Grassmannian. That gives us our first object. Now let's talk about positroid varieties, which stratify the Grassmannian. So Positroid varieties were originally introduced by Knutson, Lamb, and Speyer in 2011. I should mention Postnikov laid a lot of groundwork for these, kind of defining things called positroid cells, which are kind of the non-negative real version, versus this is the kind of complex algebro-geometric definition. Um, so maybe I'll just even give Postnikov a little shout out here. Postnikov, and he did this kind of groundwork 2006. And so Knutson, Lamb, and Speyer define positroid varieties as follows. They are varieties. The closed positroid variety is cut out by the vanishing of specific Poynter coordinates for kind of specific I, which is really nice, like to be defined by the vanishing of a variable is really lovely. These positroid varieties are kind of indexed by a number of things. The indexing set we're going to talk about today is bounded affine permutations. I'm not going to formally define it. I'm just going to give you kind of an example. You just kind of need the gist of it in your head. So a bounded affine permutation is kind of a periodic bijection on the integers. So here's an example. It's 3, 5, 4, 6, 8, 7. So to read this, this says 1 goes to 3, 2 goes to 5, 3 goes to 4, and so forth. We're using window notation. It is 6 periodic. You'll note that in a bounded affine permutation, we kind of require that all of the outputs of like element I be between I and I plus n. And then there's kind of a rule about the offset, which I'm not going to go into. So that's just kind of the intuition. I'll note that a lot of other kind of work has been done on the combinatorics of the indexing set. So these are also indexed by things called Grassmann necklaces, by Lie diagrams, by playbit graphs. There's like a whole kind of rich study of these, but we won't need that for today. So those are closed positroid varieties. Similarly, there's open positroid varieties. This is going to be, we require some Poynter coordinates to vanish and some to be non-zero. And lastly, we define the positroid cell to be the, oh, I think this, open positroid variety intersected with the totally non-negative Grassmannian, which is the kind of Grassmannian where every kind of, where the point can be represented by all non-negative Poynter coordinates. And so one thing that's not even a priori clear is from this definition is the closed positroid variety the closure of an open positroid variety? Happily it is. And more than that, the Grassmannian admits a stratification by these positroid varieties. Not to go too technical into details, but that just means that if you take the closure of any strata, it can be written as the disjoint union of other strata. And so that's really nice. Questions?
So kind of just a clarification question. So for specific I, an I is a subset of sets. It's right.
Yeah.
So for your previous example, that means uh, you would be choosing some pairs out of those which were going to zero. So you had A, B, and minus B, C, except that you if you chose like the four, then that would be in it. Is that correct?
Yeah, exactly. Like it might be like delta 1, 3 equals 0 and delta like 2, 3 equals 0. You know, could, for
Yeah.
instance, define a closed positroid variety. And exactly what those I's are, you can kind of indirectly read off from F. Kind of F gives you all of the information you need to determine what the values of I and also J are. Great
Nice.
question.
Thanks.
Okay, shall we keep going? Let's do it. Okay, so that is the positroid stratification of the Grassmannian. Let us now turn our attention to electroid varieties. So to do this, I kind of need to back up and kind of maybe explain a little bit of why the word electroid or electric comes in. So here we go. So the story starts with the story of electrical networks. You can think of an electrical network as a weighted planar graph embedded in the disk, where the edge weights correspond to how conductive your edge is. And so, like we say that here, the edge between, or kind of the wire between vertices 1 and 2 is going to have conductivity A. So that's kind of our mathematical representation of an electrical network. Now, let's kind of think about this space of all electrical networks where I have some kind of fixed number of boundary vertices. So in this case, we'd say there are 5 boundary vertices. You could also have interior boundary vertices, just this network doesn't have them, but that's certainly allowed. And let's kind of consider what happens as I allow these conductances to change. And let's just pick an edge, say D. Imagine that D is starting to tend to 0. So that is the conductivity is going to 0. Well, when it reaches 0, it has 0 conductance. So that is effectively the same as just knocking out that edge. Okay, but now let's go the other direction. And let's say, suppose we send D to infinity. Well, what does that mean? It means we have infinite conductance between the edges 3 and 5. And so in effect, here's kind of the picture you should have in your head. What's happening here is that I'm shorting out vertices 3 and 5 and identifying them. If they're infinitely conductive, they may as well be the same vertex. And then everything else kind of stays the same. So we got this here, and then we've got this. And then I could like label all of these little, this is still A, still B, still C, and still E. And you'll notice this thing here, that is not a like weighted graph embedded in a disk. It's embedded in something different. It's embedded in what we call a cactus. And so what kind of Thomas Lamb recognized in his 2014 paper is that if we want to kind of compactify the space of electrical networks, the things we need to add in are precisely these things, which we call cactus networks, or which Aditya noticed we could also call Mickey Mouse graphs and perhaps get contacted by Disney and be in trouble. And so with this, we define En to be kind of the compactified space of electrical networks, aka cactus networks, with n boundary vertices. So we want to kind of fix the number of boundary vertices. And then there's like some modulo electrical equivalence moves, things like kind of converting wires that are in this is series into one wire, doing parallel conversions, and doing what are called Y delta moves. But that's not the focus of the talk today, so you can basically ignore that. Okay, so that's electrical networks. We're moving towards electroid varieties. So then what Lamb did...
Question.
Oh, yeah.
Is the boundary also wires, or is it just for a representation, like the circle?
Great question. Yeah, it's just the representation of the circle. You should kind of imagine, like intuitively, like electricity gets fed into each of these, and then we read the currents out.
Mm-hmm.
Yeah,
and it
so this is
only
kind of
goes through the marked edges and not through the circle part.
yeah. This is the circle is just representing the boundary. Great question.
Okay, cool.
Cool. Okay, so we have these electrical networks, and in fact, this compactified space. And what Lamb did in 2014 is he realized how to connect this more directly to the Grassmannian. What he did, oh, I could move this so you could more easily see the title. This is beautiful. He showed that you can embed it in projective space indexed by these combinatorial objects called non-crossing partitions. And then you can do a linear transform and get this to projective space indexed by all n minus 1 subsets of 2n. And if I start seeing projective space indexed by subsets, the thing I should immediately be thinking of is the Grassmannian, which lives inside here. And so what Lamb showed in his paper is that this image is not only injective, it also lands in the Grassmannian. And it doesn't even just land in the Grassmannian, it lands in the totally non-negative Grassmannian. And so ultimately, the goal is to kind of define things in terms of like varieties and schemes. And so the thing that we do is we actually define the kind of Zariski closure of the image. and that's going to be what we call electroid space. And so now we have kind of, and this closure is taken within the Grassmannian. We now have the kind of following image. No, it like totally ignores all things about dimensions, but you can basically think of, we have this stratification of the Grassmannian, and we have an embedding of electroid space into it. So maybe this right here is some positroid variety. Well, let's consider this positroid variety intersected with electroid space. So in this way, kind of electroid space is inheriting maybe elements of the stratification. And this intersection is going to be what I'm going to formally define as an electroid variety. Let us go to the next page. So,
a question before you change page.
Yep.
Are allowed your edges to cross because you have non-crossing partitions?
Oh, great question. So it has to be a planar graph embedded in the disk. So we do not allow edges to cross. The reason non-crossing partitions come up has to do with the fact that you just trying to think of how much detail I want to go into here. There's the coordinates kind of, okay, I'll just show you a really quick picture. If I have an electrical network that looks like this, and I can kind of think of there as being like kind of like a spanning forest. And this kind of induces a partition. We label these 1, 2, 3, and 4. Then I'm going to get a partition 1, 2, 3, and 4. And that's kind of where the non-crossing partition is coming in from. But no, the edges are not allowed to cross. Great question. Oh, any other questions? All right. Feel free to keep stopping me as they come up. These are great. Okay, so from here, we just define things naturally. Closed vectoroid variety, we take electroid space, we intersect it with closed positroid variety, and so forth. Again, not a priori clear that if you take the closure of the open variety, you get the closed one, but it all works out, which indicates that, like, okay, we have the right definition here. So that's kind of like one of the things that we proved. Before I go any further, I just want to kind of seed something in your head for later, because I think this picture is particularly useful. And the thing I want to kind of point out is look at this diagram. This positroid variety doesn't intersect our image. And in fact, this is going to be the case. The image does not intersect all positroid varieties and intersects like way fewer. And so in that way, the indexing set of bounded affine permutations is like not the right one for electroid varieties. It like fails to capture the structure in the combinatorics. And so one question you might ask is, what is the correct indexing set for electroid space? And the answer is you want to do matchings on 2n. And so in particular, where n is the kind of number of boundary vertices. I'll talk about how these kind of relate in just a little bit, but this is going to be the correct kind of indexing set. And for those of you who know more about positroid varieties, it's very easy to get from kind of the matching to F. If I have that chi tau is equal to, then basically modulo n, tau of I is just going to be f of I plus 1. There's just like a small shift. So it's basically like you're looking which positroid varieties are actually intersected by chi n. It's the ones where if you do a shift, the bounded affine permutation is secretly just a matching. But that's a sidebar. Takeaway here is its correct indexing object is matchings. We will see this later. Okay, so that's electroid varieties. we are getting close to talking about the stratification, but I promised you, let's recall from the beginning. Positroid varieties stratify the Grassmannian. Electroid varieties stratify the Lagrangian Grassmannian. So the piece I haven't put into place here yet is the Lagrangian Grassmannian. Like, where the heck is this coming in? And like, what is a Lagrangian Grassmannian? All valid questions. And so let us go next slide and talk about where the heck this Lagrangian Grassmannian business is coming in. All right. So here we go. Just before we get on to this page, I have a reminder, which is that there's a little bit of a, you can come up, follow me here. There's a bit of a duality here. Previously, we think of the Grassmannian, or sorry, Chi-n as being kind of embedded in the Grassmannian GRn-1 to n. This is isomorphic to the Grassmannian n+1 to n, and you get this by just sending the Poincare coordinate delta I gets mapped to the complement. And so there's this kind of like just choice you have to make. The combinatorics have generally been easier using the n-1 kind of version, and just like that's historically what's been worked out. However, the n+1 version is what lets you connect it to the Lagrangian Grassmannian nicely and use a nice bilinear form. So, so just remember that that's going on. Okay, so this work was figured out independently by Chepuri George Speyer and Bychkov Gorbounov Kazakov and Talalaev in 2021. I'm going to follow Chepuri George Speyer's kind of explanation because that's the one I'm more familiar with and that we worked with in our paper. So what they did is they showed electroid space is a Lagrangian Grassmannian, which is amazing. So this kind of weird like compactified and then closure where you get this like electroid space. You're like, why do we really care about this? Maybe this is the first indication, oh, I should really care about this. Like not just because it's embedded in the Grassmannian, because we have like, this is a Lagrangian Grassmannian. And so basically in their paper, Chepuri George and Speyer defined the following bilinear form. Let's see, it works by kind of an example. This expands out x1, y2 minus x2, y1 plus x2, y3 minus x3, y2, and we can continue on. And that's kind of what the bilinear form looks like. Then from this, you can define the isotropic Grassmannian with respect to this bilinear form. It's going to be all the subspaces that for which the bilinear form vanishes on that subspace. So you take any two vectors in that subspace, and the bilinear form evaluates to 0. Note that this is a degenerate bilinear form because we have a like non-trivial kernel. These are kind of two elements in our kernel. And what these two groups went on to show is that the electroid space is exactly, when we do the n-1 to n+1 kind of shift, it is precisely the points of the isotropic Grassmannian with respect to this bilinear form. And then if you mod out by the kernel, which is going to let us kind of like subtract 2 here and 2 here, you're going to get that this isotropic Grassmannian is abstractly isomorphic to a Lagrangian Grassmannian. And so with this, we get that electroid space is a Lagrangian Grassmannian. So when we say results like we have a stratification of electroid space, what we also mean is we have a stratification of the Lagrangian Grassmannian. In case you've come across it, Ray Cartman in 2016 did some work with total positivity and Lagrangian Grassmannians. Their Lagrangian Grassmannian is different. It uses a different bilinear form and a different embedding. So like, just don't get confused. That is not the one we're referencing. We would love to be able to like synthesize these two and like translate between, but we have not been able to reconcile them yet. Maybe someday one of you will, or we will, who knows? It'll be great. Okay, questions?
So is the kernel easy to see? I mean, I know this is in the kernel, but why are these spanning? Because it feels like there should be more, might be more cancellation of terms.
Great question. I don't think I know the answer off the top of my head.
Okay. Also, I don't know if I should bring this up right now, but is the indexing of the sum from 1 to 2n? Or
Yes,
slightly
and so then you're
different?
probably worried about the plus one when
Mm-hmm.
it's taken modulo n. So 2n plus 1 becomes a 1 and you wrap around. Good to be
Very
concerned about
interesting.
the details. I swept that under the rug and you picked the rug back up. Okay. Any other questions? Great, let's keep moving forward. Okay, we have set up all the pieces. We are now ready to start talking about established results on these kind of two stratifications. So in both of these cases, Grassmannian world and Lagrangian Grassmannian world, everything started by looking at kind of the totally non-negative version. So that's really working with just like non-negative real points. And later groups were working on like, okay, let's understand this in terms of complex points. But I think it's helpful to see what's happening in terms of totally non-negative points, because I think it motivates more of the work we've done. So in the case of the totally non-negative Grassmannian, it was Postnikov who figured out a stratification into these things called positroid cells. And these positroid cells are parameterized by Playbit graphs. So what you can kind of think of is given some point here, it corresponds to kind of a Playbit graph with a specific labeling of edges. Any point in this positroid cell is going to have the same underlying graph, but a different kind of weighting of the edges. And by changing the weighting of the edges, like these guys, by kind of like shifting them like a little shifter, we can hit precisely every point in this positroid cell. So that's kind of our parameterization there. All right. Now, like, let's move forward a little bit. What kind of work of Lamb together with Chepuri George Speyer, Bychkov Gorbounov Kazakov, and Talalaev did is they said, okay, their work kind of together showed that the Lagrangian Grassmannian has a stratification into the electroid cells, which I introduced, and that these cells are parameterized by cactus networks. So kind of cactus networks are the parallel to Playbit graphs here. And so what it does is it says, okay, I have some point here, and it's going to correspond to kind of a specific weighting of this cactus network. And so I could put kind of weights on all of these edges. And as I shift the weights, I'm going to hit every point in this kind of electroid cell. As before, when I'm looking at a specific cell, it corresponds to one specific underlying graph. Okay. But let's talk a little bit about this indexing set. So I said before, it's going to be a matching on 2n. And happily, it's very easy to read off of the electrical network. So here's how it goes. I'll just describe the process to you. For any two edges that are incident, draw kind of an edge between, let's say, their midpoints. Great, so we get that. Now, anytime you have an edge that's incident to the boundary, you see if you can drop a leg. What does this mean? So here, this edge is incident to the boundary here and at 3, but let's focus there. There's two things next to it, and so I see if I can drop a leg to 7 and 8. And I just need to now get rid of these. Dropping a leg, I see that I can, and so I drop a leg. Going in the other direction, I see that, oh, okay, it's incident to the boundary vertex 3, and so I drop a leg to 6. But if I were to try to drop a leg to the other side, 5, I would cross a bunch of stuff, and so I don't drop that leg. And we just continue this process, just dropping legs wherever necessary. And with this, I get a thing that's called a strand diagram, and all of the intersections have degree 4. And from it, we can directly read off a matching. So here's what you do. I start at 1, and I follow the strand. And every time I come to an intersection, I go straight through. And this is the strand 1 to 4. So I say that 1 and 4 are paired in my matching. Now I do the same thing. I start at 2, I go across this intersection, across this, and I land at 5. So 2 and 5 are paired. 3 and 7 are paired, and 6 and 8 are paired. And we can just beautifully read off the matching from our cactus network. And these kind of matchings are going to be kind of what control the combinatorics. So this is kind of the setup, and you can see the analogy between the kind of Lagrangian Grassmannian and the typical Grassmannian. Okay, so from there, these groups kind of in both cases said, okay, let's look at like the algebraic geometry of this. So let's move from kind of these non-negative real points into the land of AG. And so let's first look at the results for the Grassmannian. So we have the following. Knutson, Lamb, and Speyer were the ones who kind of defined positroid varieties as a variety. And they went on to show that they had nice algebro-geometric properties. They showed that you have actually a stratification. They showed that the cell is dense in the open positroid variety. They show that the open positroid variety has nice properties. It's irreducible, it's smooth. It has easily calculated dimension. It's just based on whatever f is. They showed that the closed ones are reduced, irreducible, and normal. And lastly, showed that there's a Frobenius splitting and that the positroid varieties are not only compatibly split, but they are precisely the compatibly split subvarieties. Then building on this, and kind of basically, if you don't know what a lot of these words are, like TLDR has a lot of nice algebro-geometric properties. That's like really the takeaway here. And then what kind of was built on this is Muller and Speyer then kind of showed that you can embed algebraic tori as dense open subschemes of open positroid varieties. And this is kind of deeply tied to kind of the cluster structure. And then excitingly, recently, Gorski, Kim, Scrogan, and Simmental kind of constructed a splicing map, which kind of embeds a product of two positroid varieties indexed by skew diagrams into kind of a single positroid variety. And under certain conditions, this is actually an isomorphism, which is also like a really lovely result. And so that's kind of the positroid varieties. So that's kind of the existing work. And now I'm ready to talk about like what we've been working on. And so basically we looked at these results and we said, okay, which of these are going to extend to electroid varieties? Like let us understand the algebra geometry, or the algebraic geometry of them. And so this is what we have found. This is in a paper that is about to be published, like, or I'll put on the archive, hopefully like in like the order of a week, couple weeks. And we basically proved that almost all of these same things hold. So we can walk through. We have a stratification, the Zariski, the cell is Zariski dense. It's irreducible smooth and has expected dimension if we look at the open electroid varieties. And in particular, the expected dimension is really nice. So if I'm looking at the open electroid variety indexed by, say, some matching, maybe, or that looks like this, its dimension is simply the number of intersections or the number of crossings when I draw kind of a minimal, like, when I draw kind of a minimal matching diagram. So it has, this guy would have dimension 3, which is really lovely. For the closed varieties, we showed that they're reduced, irreducible. We could not get normal, but we did get kind of a weakening, which is regular in codimension 1. So kind of says, behaves nicely. The kind of singularities are occurring in codimension 2 and above. As before, we have a Frobenius splitting. The electroid varieties are compatibly split and precisely the compatibly split subvarieties. We can embed algebraic tori as dense open subschemes of the open electroid variety. And we have a splicing isomorphism, which respects the stratification on both sides. And here, what it kind of says, how it works is if you're indexed by kind of two matchings, maybe that look like this, and like this. Whoa, that's a bad picture. Then it's going to be isomorphic to the variety indexed by a matching where you just like mash the two together. So you put that and that, and voila, they're good. All right. So kind of this was our big result. I'm going to kind of spend the last, say, 15 minutes of the talk, when do we cut off? Do we cut off at 50 or 45 or 55? When is?
Usually around 12:50, but if you need a few extra minutes, you can definitely do that, and then we'll leave it open for
Oh no, I
questions.
have a flexible endpoint, so I can hit like 50, hopefully right on. Great. Cool. So I'll pause and say, like, before I kind of talk about so the last part of the talk, I'll talk about kind of what are some of the combinatorial guts of this? Like, what are the kind of combinatorial structures that kind of let us prove some of these results? Because underlying all this, like, AG is really just a ton of combinatorics. But maybe first, any questions? Great. Okay. So, okay. The combinatorial tool underlying literally everything is matchings. Okay, it's not literally everything, but really at the end of the day, we keep like seeing that matchings is what's gonna like kind of control these objects. So I'll kind of give you a brief overview. Let's consider the matchings on 2n or 6. So this is going to be the case when n is equal to 3, which corresponds to chi3. So remember, this is coming from originally electrical networks with 3 boundary vertices. And so we can kind of consider the set of matchings on 6, and we can put a partial order. And this partial order is based on uncrossing. So what do I mean by that? Let's kind of consider two strands that cross, these two. Well, there's kind of two ways that we could resolve this crossing. We could resolve it like this. And I see that if I do that, what I'm going to get is I'm going to get this guy over here. There's also another way that I could resolve it. And so then we say that this here is less than this here. And in fact, in this case, it's a covering relation because I'm just increasing the number of crossings by 1. The other thing I could do is I could resolve it in the other direction. And I see that that's going to give me this right here. And so this uncrossing gives a partial order on the poset. And in fact, it gives you like a graded partial order. And this partial order like really is kind of, that tells us the structure of the stratification. So what do I mean by that? I mean that if I take some closed electroid variety, I can rewrite it as the disjoint union of open electroid varieties indexed by all matchings that are less than or equal to kind of the OG matching. So let's just look at an example because I find examples are nice and helpful. Oh, nope, wrong one. Okay, so let's look at this guy here. So this is our chi tau, and I want to decompose it into open electroid varieties. Well, I just need to look at everything less than it. So I see that this is less than it, this is less than it, this one, and this one. But I need to go further. I've got this one. Ooh, how good am I at seeing these? And there's one more. It should be, I'm trying to figure out this guy. And so all of the shaded purple matchings, if I like then look at the open positroid varieties indexed by them and take their disjoint union, that's going to give me the closed electroid variety indexed by tau. And this is what our stratification is. Okay, so that's nice. That's kind of how the stratification works. There's another kind of observation, because we have, and here's the observation. I'm going to just erase some things to make this cleaner. Let's look up top. If I look up here, the closed variety is actually just the entire electroid space. And the entire electroid space is a Lagrangian Grassmannian. And there's things we know about the Lagrangian Grassmannian. We know what its dimension is. We know that it's smooth. We know that it's irreducible. And so here's an idea. What if there were kind of smooth preserving operations as I went through kind of along a kind of covering relation? Like, what if that preserved smoothness? And then you'd see that I could kind of distribute smoothness down through lower dimensional varieties by kind of cleverly moving along these cover relations or some subset of cover relations. And that's what we recognized, and that's what let us prove that the open varieties are smooth, irreducible, and have expected dimension. So let's look at that. So here's the idea. And this motivates, so that kind of observation or kind of realization motivates the following definition. So if we have some covering relation between matchings, we say that it forms an I-crossing pair if tau prime is formed from tau by taking two strands, I and I plus 1, so adjacent strands, which are disjoint and uncrossed, and crossing them in a particular way. So I think it's much easier to just do an example rather than me add more words to that. So what we have here is we have I and I plus 1 are two different strands that don't cross. And then we cross them in the following way, connecting I to what used to be tau of I plus 1 and connecting I plus 1 to what used to be tau of I. And this is like a very particular kind of covering relation. And when we realized, preserves a lot of nice properties. And the reason it preserves it is as follows. If you have an I-crossing pair, then what you get is you get an open embedding from the smaller variety crossed with C star into the larger variety. And in particular, it's onto a dense open subscheme. And so what that lets you do is it lets you say, okay, if I know that this is smooth, then I'm going to get smoothness past to this guy. And then I'm going to be able to say, actually, smoothness passes to this guy because it's just a product with C star. And so I can kind of pass smoothness along via I-crossing pairs. Similarly for irreducible, similarly for dimension. And so as a corollary of this process, we get that the open electrode varieties are irreducible smooth and have dimension equal to the number of crossings. And the basic idea of the proof is, well, first, recognizing that the top dimensional kind of closed variety is a Lagrangian Grassmannian. Thank you to all of the former mathematicians who proved it's a Lagrangian Grassmannian. And then we induct down. We use the proposition, and we recognize that every every matching can be achieved from kind of the maximal matching via uncrossing adjacent strands. And when you put those three things together, and are careful with some other stuff, you get the result. Questions?
Is there an easy argument for why this poset of matchings has a unique maximal element? Or does it always? Or
yeah, great question. So we basically say there's going to be, right, the maximal, let me see if I can do this. And if you're happy with it, then we've found an easy argument. There is always a maximal element, and it's the element formed by kind of connecting I to I plus n. And so in particular, maybe we just go to a picture here. It's basically where all strands cross every other strand. So you have n strands and you want them all to cross each other. And I think you can pretty quickly convince yourself the only way to do that, to have like n strands which all pairwise cross each other when drawn minimally, is as if they kind of connect across the circle. It
Okay.
certainly
Sorry. Is there any choice on, so every strand has to cross every other strand, but if I have already some crossings, isn't there any choice on how to navigate through these crossings?
Oh, yes. So we don't actually care about how it's right. There's different kind of representations of the matching and ways of drawing it, but that doesn't actually impact the ultimate matching. So I'm drawing pictures, but yeah, this is good. So this is one way of drawing this matching, and it really represents one going to four, two going to five, and three going to six. But as you've kind of pointed out, there's another way I could draw this, which is I could instead go like that. And we don't really care about that. I think visually, to understand uncrossing, it's helpful to draw pictures, but we just care. Ultimately, a matching is just defined by that information here.
Okay. Very interesting. Thank you. But does it define then the same class of electrical graphs? How were they called? I don't remember. Because I thought they were on the geometry, the matching.
You have if I'm understanding correctly, you have identified another thing that I swept under the rug. Uh, these both define the same electrical network, but in here, I'll just draw a picture. These two electrical networks are actually the same under electrical equivalence, which is the thing I just snuck in at the very beginning. And in fact, if we draw their kind of matchings, let's see if I think these are going to give us two different looking matchings. Yeah, it's the same matching, but it looks different. I've just kind of like pulled one kind of strand through the other. Um, and and so yeah, these define the same electroid variety. There is just like different ways you can kind of pick to draw your network. And Thomas Lamb in his 2014 paper gives like a very rigorous, nice kind of explanation of exactly how you can manipulate the graph. Yeah, good catching on to that. Did that answer your question or did I miss something?
Yeah. Thank you very much.
Yeah, of course. Yeah, so let's see. Great. So matchings underlie everything. I think for the sake of time, we basically hit all the things. I think, yeah, the matchings is like the combinatorial guts of what's going on with electroid varieties. And like being able to manipulate them and understand how they kind of change other, like which Poincare coordinates are vanishing, etc. That's kind of like the heart of the combinatorial work of this paper. I'm going to skip the next couple slides. They're just more evidence of why matchings determine everything. These are my references, if you want to look at any of them. And lastly, thanks for listening. It was fun to share with y'all.
Thank you so much, Mia, for such a wonderful talk. Are there any additional questions?
Could you go back to the thing where you were putting one matching on one side and the other matching on the right side?
Oh, yeah.
Um,
That one?
Before this, like I think it was multiplication where you had this
Oh, this one
tau.
here.
Yeah. So what is so is this like a direct product? What is that multiplication?
Um, it is it is oh God. It's just like a product.
Okay. Yes, my follow-up question was like, are there any sort of polynomials associated to what we are looking at? And somehow you could describe like a multiplication structure because expressing one into the other with this sort of stratification feels to me very much like basis expansions. And so if there are,
Yes. So I think you can, right. When we are looking at kind of how you prove this, there's a couple lenses um, with, yeah. So you can basically describe if you take some kind of polar coordinate here, you can kind of describe it and split it up into kind of like two pieces here. Like the eye kind of splits up into two pieces. Um,
hmm,
and like one of these subsets is on kind of one set of numbers, and one of them is on kind of the other set of numbers. That's like
right.
a little hazy, but that's kind of the gist of it.
Hmm, hmm, hmm.
I don't know if that was getting at your question or not.
Yeah, I think I was asking more of maybe you could associate some sort of like weights to these varieties and then your poset structure. Uh, and so when you're doing this multiplication, this is actually like polynomial multiplication. And when you're doing the stratification, that is maybe expanding one polynomial into another basis of polynomials. And so if there's a,
Mm.
like in the case of, symmetric functions, all of the representation stuff is being done on the polynomial side. Is there a variety conversion to polynomials?
Ooh,
That
okay. I would
question.
have to think about more about like precisely this, but I think that's yeah. Okay, that's an interesting idea.
Mhm.
Any other questions for Mia? If not, then let's thank her one more time. I'll go ahead and stop the recording.